from this analysis, we will obtain not only the summary data for the entire slide, but also outputs for every single cell in the analysis, which we will then use in our spatial analysis. So the final part here is we really want to probe where our immune cells are in relation to the tumor. And this is becoming increasingly important, as Katie showed in that slide. In the field, many people are very interested in the spatial relationships of cells in the tumor and microenvironment. And we really have the tools in HALO to capture these spatial relationships. So the one I will focus on today is infiltration analysis, where we can quantify immune cell infiltration out of the tumor at a defined tumor stroma boundary. So now I'm going to move into my live demo of the basic steps that we perform in HALO and HALO AI to validate an assay for our immuno-oncology study that can then be deployed in HALO AP. So I'm going to switch over to my HALO application here. And today, really in the interest of time, we'll be giving you a very brief overview of the steps in our workflow. If you would like a more in-depth walkthrough of each of the algorithms and all of the parameters that are optimized in each of these algorithms, then please visit our Indica Labs learning portal at learn.indicalab.com. And there we really have a wealth of tutorials, webinars, and user guides that take you step by step through the entire optimization procedure for all of the algorithms that I'll be showing you today. But for this short demo, I am going to be showing you a study with 3 images that are already open here. And these are 3 different biopsies for different tumor indications. So we have a colorectal cancer sample, we have a non-small cell lung cancer sample, and we also have a renal cell carcinoma. So as you can see, I have already performed our annotations to include the area, the region of interest for our analysis here. That is a solid yellow line. So it includes really the bulk tumor and the tumor-associated stroma. I've also used exclusion annotations, these dotted lines here, to exclude these tissue folds and some staining artifacts that are seen on the slide, so those do not interfere with our analysis. Now, the main goal of our study is to really quantify the immune cells that are invading the tumor. So if we take a look at the staining here, you see we have CD3 cells stained with DAB, so those are the brown stain here. And then we also have hematoxylin as a counter stain to identify the nuclei. However, we do not have any tumor marker stain on this slide. So we really have to rely on the tumor morphology to be able to identify and delineate these different compartments to find the tumor, the stroma, and any other classes of interest. So in order to do that, we really need a robust classifier. And for that reason, we will be using an AI tissue classifier today. So let's go into that tab here, the classifier tab. And we will start looking at our AI classifier. So you'll see in this classifier type list, I have all of the classifiers available, but what I'm going to do is actually load a classifier I have already been working on and just point out some of the more important features of our workflow. So what you can see here is that the first thing you'll see is that there are a number of classes that I have added to our classifier to identify all of these classes in our tissue. So the first one is our glass class, which is in gray. We have a class for necrosis and red blood cells in teal. So we can actually exclude these areas from our analysis. We have a class for normal tissue. So that's anything on the slide, like in this lung sample, we have some normal airways here. We can identify those. We have a class here in green for stroma, and then tumor is in red. So you'll see there is a number of training examples I've already provided for this classifier. One very important thing to remember is that you want to add training to the classifier that covers the entire spectrum of tissue morphologies and indications, as well as staining patterns in all of your samples. So you can see I've added these training regions to all of the cases in our study to cover all of the variability that we may see between images. So once you've added your training regions, typically